everyone. We're here with Andy Pavlo, professor of databaseology at Carnegie Mellon University, who, like, you might know him from great lectures on YouTube, freely available in database management systems, or the most recent vaccination database series talks on different database systems, which he doesn't present there, but he invites speakers to talk about different databases and storage systems and things alike. And today, Andy will talk about database research turned into a startup company called Autotune, about applying machine learning to tuning databases for better performance. Welcome, Andy.
Hey, thanks for having me again. Good to see you again, man.
Yeah, good to see you too. Yeah, the last time we spoke at Hydra, actually, so not at this conference, but yeah, that was a very similar setup.
Yes.
So how's your Autotune things going?
So we just launched the sort of self-service version of Autotune last week, and we'll be announcing GA later this week. So it's pretty exciting. I definitely have learned a lot, and sort of what this talk is about is the things we've learned that going from the research side inside the university and trying to get this run out in the real world. The things, what are the problems that we didn't expect to face?
Are you dipping your toes into industry a little bit more?
So if the question is whether I'm leaving Carnegie Mellon, no, I'm not leaving Carnegie Mellon.
No, that's not a question.
I'm asked that a lot.
Oh, wow.
But no, so I like to think that the research we do at the university is always grounded by what's happening in industry. And I think it's important because when you do database research, not only are you sort of competing against other academics at other universities, but you're also competing against the major tech companies, IBM, Microsoft, Amazon, Google, and so forth, and Oracle. But then there's all these startups that have very interesting database systems that they've been building. So part of what my lecture series that I do on YouTube is about is there's so many things I can't possibly just learn it on my own by going out there and trying to read everything. So we invite the speakers to come talk about what they're actually building. And so again, that sort of grounds us to make sure that we're solving interesting problems and not just trying to make TPCC go faster for no good reason with unrealistic expectations.
Yeah, the vaccination talk series definitely kind of widened my horizon. I didn't expect people solving those kind of problems with databases and all kind of solves distributed SQLite or whatever.
Yes.
Where is it coming from?
Yes.
I did not expect that.
Yes.
Okay, so let's start with the actual talk. So to Andy to present the Autotune and lesson learned from machine learning for database tuning.
Awesome. All right. So the way we're going to do this, that's for everyone in the audience. If you have questions, I'll make pauses as we go along, but feel free to send a message to Andre and he'll convey them to me. All right, guys. So as I said, today we're going to be talking about the things we've learned of actually taking the Autotune project out of academia, making a startup, and actually trying to run it on real databases to optimize optimize database systems using machine learning. So for the sort of outline of the talk, we'll begin with talking about the basic background of Autotune and configuration tuning. And we'll talk about how the Autotune architecture actually works. But then we'll spend time now talking about the things we've learned of actually trying to get Autotune run outside of the lab, run on real databases, running production. And one of the main things that you'll find out from this talk is, turns out the machine learning stuff is less important. It's working with databases, understanding what databases are actually trying to do turns out to be the more tricky thing. And then I'm going to talk a little bit about some fun stuff we're doing, going beyond databases, looking at things that are not just things that make Autotune interesting and fun. Okay, so Autotune is focused on knob configuration. Yes. Okay. So Autotune is focused on knob configuration tuning. So a knob is a runtime parameter that every single database system exposes to you that allows you to control the runtime behavior of the system. So think of buffer pool sizes, caching policies, log file sizes, and so forth. And the reason why these knobs exist is because as the database system developer was building the system, at some point they had to make a decision on how to set a certain parameter, like how big should my hash table be when I do a join. But then rather than putting a pound define in the source code and and just letting that be it's a single value for all perpetuity for the database system. They instead expose it as a knob that allow you as an administrator or a user to actually set that value, because they assume that somebody else is going to come later on and is going to know exactly how the application wants to use the database system, and could therefore be in a better position to set that knob. And of course, this is problematic because setting these knobs is non-trivial. So what are people doing today? Well, a lot of times we find that people are not maybe aware or don't know how to actually tune configuration knobs. So instead, when they're running their database in the cloud, they just keep throwing money at the cloud vendors to increase the size of the database instance. They're doing essentially scale vertically, and try to assume that's going to solve their problem. But that'll only get you so far. So this is a study we did a few weeks ago where we just took the TPCC benchmark running on Postgres RDS, and along the bottom, you see we're scaling up the size of the instance. And at some point, when you get to M5 8x large, beyond that point, the workload doesn't get any faster, even though you keep giving Amazon more and more money. So we see this pattern all the time. People just think like, oh, I'll just keep scaling, and I don't worry about how to tune these knobs because the database system will scale vertically or scale with me with my hardware. Or they assume Amazon has maybe already tuned the database for you, which is not the case. So if you have a lot of knobs, this is very problematic. And how they're actually going to interact with each other is difficult to understand. So at this point, the number of knobs that these database systems have grown so much in the last couple of decades that this is beyond the sort of reasonable expectation of what a human can actually manage. So this is a study that we've done a few years ago where we just looked at the last 20-year release history of the two most popular open source databases, Postgres and MySQL. And for every single new release, we just look in the documentation and counted the number of configuration knobs that they expose. And you can see here that at the beginning of the century, both MySQL and Postgres had less than 100 knobs, but then 20 years later, MySQL grew by 7x and Postgres grew by 5x. Now, not all of these knobs will affect performance, right? Some of these knobs are log file names, directory names, port numbers, host names, right? Things you're not going to want to actually tune to get better performance. You need to set those once in order for the system to actually operate correctly at all. But there's still enough of them that will affect performance, and wrapping your head around how to tune them for every application, every database is non-trivial. So what are people doing today? Well, you essentially have 4 choices of how to tune these knobs. The first is you can kind of DIY it, do it yourself. And this is where some DevOps person or maybe some programmer that knows something a little bit about databases will just Google search terms like MySQL tuning, Postgres tuning, Oracle tuning, and you're going to find a bunch of these blog articles that basically give you some high-level hints on maybe how to tune a small number of knobs, maybe like 4 or 5. And these are usually based on conventional wisdoms like use a certain amount of memory for the buffer pool in the database system. But of course, then these are sort of general purpose, high level. They're not tailored for exactly the application that's running on your database that you want to tune. And actually, oftentimes we found in some of our experiments that the recommendations in these blog articles are actually incorrect. You want to do the opposite on what they prescribe. All right, so maybe instead of having like the one person who knows a little bit about databases on your team try to figure this out, you try to throw some money at the problem, and you hire a DBA who understands database systems and has some background in knob tuning, and have them try to figure things out. But the problem is this doesn't scale, and these are human beings, and therefore they're expensive. So I apologize for not translating this into rubles, but in the United States, the average salary from a few years ago for a DBA is $96,000 a year. Again, that's the average across the entire United States. Certainly on the East Coast and West Coast, or more tech-heavy areas in the country, you're going to pay a lot more for DBAs. Right? And think about what you're doing. You're basically paying for somebody who can babysit the database system software and help you maintain and optimize it for you. But again, this is not scalable. If you have thousands of databases, you just can't hire 1,000 people to watch them all for you. And the DBAs you're hiring also too are not just doing knob tuning. They're doing a bunch of other things, like they're doing SQL tuning, picking indexes, crash recovery plans, and so forth. There's a lot of things that they're doing, and knob tuning is usually a low priority, even though they know it's important. So another alternative is to use these rule-based tools. So something like pgtune or MySQL Tuner, And these are scripts where they've hard-coded logic inside them that can do some basic tuning parameters or tune some basic parameters for you. Similar to those blog articles, now they're just codified in code. So you can punch in, like, I have this many CPUs, this amount of RAM, and they spit out some basic recommendations. But again, they're not tailored for your application. They're just using sort of conventional wisdom to set these parameters. So what I'm arguing for today is that you should be using machine learning based tools that can automatically learn how your application is using the database system and can understand how the application's behavior changes as you set these knobs in order to set them correctly for you, right? And the idea here is that because now we remove the need to have humans, or if we can tailor each single application or each single database instance exactly for the applications using it, we don't have to worry about inefficient configurations or not being able to scale for really large fleets. So this is what Autotune is. So Autotune is an automated database tuning service that's going to use machine learning to automatically understand how your application is using the database and knows what knobs that are available for to set, and can come up with an optimal configuration that are either improve performance or reduce your hardware and software costs. And as Andre said, this is based on research that we've been working on for several years now at Carnegie Mellon here in Pittsburgh. And now we spun it off last year as a startup, and we're making this available to people outside of the lab. So currently, Autotune supports Postgres and MySQL. And right now we're focusing on running on AWS, so either RDS or Aurora. We've done on-prem deployments, which I'll talk about today. We can also potentially support Microsoft, Google, and IBM cloud services. Just, most people are on Amazon, or there's a lot of databases on Amazon, so we're targeting that first. So it's always risky to do this in a live talk, but I'm going to try to give a demonstration of Autotune to see how it works. And so for this, we're going to tune a Postgres database running on Amazon RDS, and we're going to run this sort of industry standard TPCC workload using the old DBMS framework to run transactions on the database. And we're going to start off initially with the default configuration that Amazon gives you. So Amazon's already done a little bit of tuning. It's better than like the default you get from Ubuntu, but it's still not ideal. So we're going to start with that as the beginning configuration. And then while I give this talk today, Autotune is going to observe the workload, make changes to it, and try to come up with new configurations to improve performance. We're actually going to run the two databases. We're going to run one with the Autotune is going to actually configure and tune, and then we're going to run one where we don't make any changes. We'll use that as the baseline so you can see that over time that Autotune is actually making things better. So to do this, I'm going to stop sharing. I need to extend screen, and that breaks screen share. All right, so let me come back and share again. Okay. So I need to log in again. Oh, we're in. All right, so we're going to go ahead and create a new database. We're doing Postgres. And I have instructions on how to do all this. Oh, sorry, you cannot see this. All right, so we're going to put in our Amazon identifier. So put that there. And we're going to be in US East 2. And then we'll call our database name TPCC. So these are the basic information you need to provide to Autotune in order to connect to your database. And then it's going to ask you to go ahead and create a user on the website, or sorry, in your database that has minimal permissions to make changes to collect the information from the database system itself. We're also going to collect to Amazon CloudWatch to retrieve additional OS level metrics, but we also get the things that the database system generates on its own. So right now it's going to Amazon and trying to connect itself. All right, so now we can skip all this. This has all been set up for us. So now we got to go back and go to our database. We're going to edit the tuning options. So we're going to enable that we want Autotune to actually optimize the database. We're going to set the tuning interval to 240 seconds. So this is how often Autotune is going to go check to see is the database operating correct. You know, it goes how often goes check to see what's the performance of the system. And then we will go ahead and set this thing. This is just the ARN where we go be able to set the parameter groups. And there's a bunch of stuff we have to do to give permissions to do this. So this has already been done for us. Sorry, it's a bit pokey here. All right, and then we're gonna go ahead and just enable all the knobs we want Autotune to tune. So these are all the ones that it has recommended for us. And we're just going to go ahead and let Autotune set them. And then it's already sort of set up some basic boundary information of what set these values to, because it knows what our instance size is. It knows what we're, what the hardware resources are for the database, and we go ahead and do that. So while this is running, we'll come back to this and see how it works out. But meanwhile, we have our monitoring database that we'd be able to connect to, and we see what the current performance is. So again, we're going to let this run while I give the talk, and then we'll come back to this in a bit, or at the end of the talk. So let me go back and return to PowerPoint. That one always breaks. Okay, so how's Autotune work? So you have the you have your target database. Yep, thank you. Yep. Okay, so you have your target database that you want to tune, and you provide Autotune with some basic information to log into it and access it. Again, this is minimal permissions you need to go get the runtime metrics of the database system. So these runtime metrics are pages read, pages written, locks held. Right? These are not any user tables. It's not any of the queries. So there's no sensitive information. This is enough for us to be able to figure out what the application is actually doing. Right. So then now this is put into the Autotune service. You download a Docker file that runs in the that connects to the data center it runs in your network, connects to the database system in order to retrieve the latest metrics and the latest configuration. Again, we're just doing this using the standard AWS calls to get the parameter group or CloudWatch, as well as SQL queries that retrieve this information from the database system directly. The agent then ships that over to our service running at AWS. We store this in a secure repository, and along with all the other training data we've collected from previous databases we've tuned. And then we have a compute engine that then can train statistical models that predict how the database system's behavior will change as we start making changes to the configuration knobs. We then, the compute engine then uses these models to generate a new configuration that it thinks is going to improve performance. We then spit that back over to the agent, who then applies it to the database, and then we observe whether this helps us. And sort of the feedback loop here is that we generate new configurations, apply them to the database, see whether they're actually helping us, and allow the models to converge to what it thinks is the optimal solution. So I've already said sort of the two key things about this. Right? There's a feedback loop. So every time we try a new configuration, we're getting more training data, we're improving our predictions, improving the efficacy of the configurations that we're generating, and we can see that we're making things better. And the other important thing is that we don't need to look at any sensitive information about from your database or from your queries. We just need these metrics for us to figure out how things work. And for the deployments we've done in Europe and abroad that have GDPR issues, there's InfoSec people have looked at what we're sending back to us or sending back to our service, and they've been okay with it. So while the demo is running, I want to show some previous studies we've done of this. So this is going to be running TPCC benchmark again on RDS, but now we're going to run it on 2 instance sizes. So the first one is going to be M5 4x large, and the next one will be a 2x large. And this one has 4,000 provision IOPS and 2,000 provision IOPS for this one. So we're going to compare against, again, the default configuration that Amazon gives you, but as well as one of those rule-based tuning tools. This one's called PGTune, where again, you punch in some basic information about how much RAM you have, how many cores you have, and then in your disk type, and maybe what the workload looks like. and it generates a configuration recommendation for a small number of knobs. So the main takeaway from this graph is, first, that we see on the larger instance size, again, the default configuration from Amazon is always terrible. But again, a lot of people still use that because they don't know that they should be changing it. And that Autotune can get over 2x, can achieve over 2x performance improvement on what Amazon does. And then same thing for the smaller instance. Again, we're still getting a 2x performance. But the key thing about this is, though, you see here on the smaller instance, we're getting back basically the same performance as what you got in the larger instance using the default configuration from Amazon. But now if you think about this first instance costs $17,000 a year. The second instance is half price. So with Autotune, you can either get like double the performance for this particular workload, or you can downgrade to a half price instance with less provision IOPS and still get the same performance that you were getting before. Right? The same models can achieve both of these results. So here's the same experiment now for MySQL, then MySQL version 8. So again, you see that the RDS default configuration is always terrible. MySQL Tuner actually does pretty good on the larger instance size, but again, Autotune always outperform it. And then in this case here, what I really like about it is that we're getting double the performance on the cheaper instance size, and we're paying half the cost, right? So again, you can have your cake and eat it too. With Autotune, you can get better performance and potentially pay Amazon less money. And again, we don't need to look at any user-sensitive information. We don't require any custom plugins into your database or new custom extensions. We don't require you to make any changes to the application, right? And this is all being done through the standard interface that the database system or Amazon exposes to you. Right, so these are similar to the results that we were seeing when it was a research project in the lab. But again, this is running TPCC. Some may say this is not representative of what most workloads look like in the real world. That's not always true. I think TPCC is pretty good. But we wanted to see for production environments and other workloads beyond TPCC or beyond the other synthetic benchmarks that we have access to in the lab. Does Autotune actually really work? And so we, through total luck, we met the guy that runs all of Amazon's machine learning AI division. He came to Carnegie Mellon. I got 5 minutes of his time to ask him, to thank him for giving us a couple $1,000s to run our experiments on EC2. And he was like, "Great, can you write a blog article for us? We just started a new Amazon AI blog. we need articles." So we wrote a sort of summary piece for them in 2017 that explained what Autotune was and talked about the recent research publication we had come out in SIGMOD. So when this thing came out, all these nut jobs started emailing us and saying Autotune is the greatest thing ever. We have this exact problem. A bunch of people wanted to do startups with us. They were all weird and crazy, but this is not what we were looking for. We got a lot of these, but then eventually we got this great email here from somebody in Paris, working for a major bank, who said, "Hey, look, we have a huge Postgres installation running in our data center in Paris. We're not doing any tuning on it. It'd be great to be able to run Autotune on it." So we took them up on this offer, and this was the first real field study we've done of Autotune outside of the lab. So as I said, they reached out to us and said they had 1,000 Postgres databases running on-prem in their data center. And what's interesting about this environment was they had a sort of self-service or self-provisioned interface that allowed the different IT groups to spin up Postgres instances on their own without having to make requests. Similar to how you can fire up RDS instance without having to ask anybody. They had this internally for their for their data center for their IT group. And what would happen is you would specify how many cores you wanted, how much RAM you wanted, and there's a drop down to say what the workload looked like. Is it OLAP? Is it OLTP? Is it HTAP? And they had a basic sort of handwritten configuration for each of those different workload types, but they weren't doing any optimization or any custom tuning the way Autotune was doing across the entire Postgres setups. So they wanted to use Autotune for that. So this was a research collaboration. They had an on-site master student in Paris, work with us to get Autotune up and running for them. And after a few months, they got it working. And they said, "Okay, let's go point it at the Postgres databases that are running in production." And then, a few days later, they came back to us and said, "Well, we made a mistake. We told you we had 1,000 Postgres databases. The real number was 1. So what happened was the bank a few years before had this big initiative where they said, across the entire company, we need to start using more open source software. So that meant for every single new project, the manager had to put in a budget justification what open source software they were using. So the word got around the bank that if you just click the checkbox on the form and say, I'm going to use Postgres, you would then spin up a Postgres instance. You never put any data in it. You never ran any queries in it. And you just use Postgres use Oracle and paid Oracle like you normally would. No one would ever check. No one would ever care. So they literally had 1,000 Postgres databases running across their data center that were completely idle with no data, no queries. So that was a bust, right? After all that work. But then they came back to us again and say, okay, well, we're primarily an Oracle shop. Can you make Autotune work on Oracle? So we had a master student on our side spend some time porting Autotune to make it work on Oracle. Again, we don't have to make any changes to the machine learning models or the algorithms. The machine learning stuff doesn't care that this data is for the next data. It's just numbers. But it's all the tooling up front, as we see in a second, in order to interact with the database, understand what's going on. That's where the time we spend all our time. That's the tricky part. So they gave us a 1 terabyte database that they had already tuned in production, doing SQL tuning, knob tuning, index tuning, and so forth. And nobody was able to make a good dent in performance. So they wanted to throw Autotune at that and see what it could do. So unlike before with TPCC, where I'm showing you're trying to optimize throughput, or maybe sometimes you optimize P99 latency, for Oracle, they want to optimize this thing called DB time. And this is a proprietary or a Oracle-specific metric that is a summation of a bunch of different wait times throughout the system. We were told that this is what all the Oracle DBAs use to measure the performance of the database system. So we had, again, the machine learning models don't change. We just have to make it so we can collect this data and then feed that as the objective function we were trying to optimize in our algorithms. So I want to talk a little bit about what the setup looked like, because I want to show what we did in this field study, and you'll see how it compares to the next field study. And this shows you different ways that you have to use something like Autotune, right? It's not this, you can't just click a magic button and things automatically go faster. There is some work to be done to make sure that you're not interfering with the production workload. So for this, the way we did this was they gave us a snapshot of a database that was running production, and they provisioned a bunch of VMs in their private cloud that was running the same hardware that was running in production. And then they also captured a workload trace from the database running production, which basically it's a capture of 2 hours worth of queries that were executed, so that we can run, we can load the snapshot on a spare machine, load the snapshot, replay the workload over and over again, and that was an easy way for us to measure whether we're actually making things better or not. So the way this works is for the agent and the driver, it would first start up a database system, but then immediately check the logs and make sure that the database system started correctly. We'll see in a second. There are some cases where you can set the knobs to incorrect values, and the database system won't start up at all. It'll throw an error and crash. So you have to make sure that to check whether that happens. Then we're going to reload the database from the snapshot we've collected, and that puts us back to the same starting point for every single iteration, every single trial of a new configuration. But then we would actually run an I/O micro-benchmark using FIO to measure what was the disk speed for the database at this moment we did this configuration. We had to do this because every database that we tested on was running in a shared disk setup, where all the Oracle databases had to read and write data from a shared NAS in the data center. And they had to do this for like security and regulatory reasons. Right? Each database was not allowed to write to local disk. It always had to be written to a centralized storage unit. So the problem, though, is because this is now a shared network, we found that we would see wild oscillations of the performance of this shared disk, and that could affect the algorithm's ability to identify whether a good configuration was whether configuration was actually good or not. Right? There would be times where we say we tried a configuration that I thought would make a big difference, but then it saw really bad performance, and that was because the shared disk, all of a sudden got busy or got contended, and things got slower unexpectedly. So just give you an idea what these results look like. So this is us running the random read micro-benchmark for FIO, and you can see that the blue line is the local disk, but again, we can't store the database on that. And the red line is the shared disk, and you see that near the end of the 3-day period we were measuring this data, there's all of a sudden a huge spike where the I/O latency increased by two or 3x. As I said, like we had to account for that in our machine learning models to understand, okay, did we see bad performance because the disk got slow or because of the configuration actually was bad? And so we tried a bunch of tricks to try to normalize the data to account for this. What we actually found is that none of that actually make a difference. It just, if you just collect enough training data, this will smooth out and this will go away. But we needed to do this in order for us to understand as humans what the machine learning models were actually doing. Then the next step was that we're going to collect the metrics. As I said, this is just using the standard SQL API that every database has to get these different runtime performance counters. Then we're going to run our workload trace that we captured from before. And so we captured a 2-hour trace, but we would only play 20 minutes because, as we'll see in a second, depending on what configuration we're using, that 20-minute trace may take hours. And so if you had a 2-hour trace, that could take potentially a day if you have a bad configuration or other issues. We'll see in a second how we account for that in a few more slides. All right, and then I'm going to collect the metrics again. And then now we're just going to compute the delta between before and after we ran the workload. So like a lot of times these metrics are just incrementing forever. So you want to know how much disk that I read when I run this workload. You just subtract what it was before, what it was after from before, and just get the right value. So then we ship this over to the Autotune service along with the current configuration. The machine learning models are going to crunch on that, generate a new configuration that we send back over now to the driver, who then installs it and then restarts the database. So we can restart as many times as we want for this database because we weren't running production; we were running on spare hardware. So I'm going to show one graph for this. So we tried a bunch of different combinations. We actually tried a bunch of different variations of machine learning models to generate the new configurations. So the GPR, the Gaussian process regression, is what the first version of Autotune was based on. Then we had a deep neural network that we built, and then there's a reinforcement learning approach called CDBTune at Xinhua and Tencent in China. And so we tried all of them on different numbers of knobs. And so this line here represents the default config that they had originally for the database system. And as you can see across the board, we're always able to get better performance than what they were running before. But there's not one algorithm that performs better than the other. And in some cases, we found that like tuning fewer knobs actually made a bigger difference because each experiment took days to run. And so if you had less knobs that you had to consider while you were running this experiment, you can converge more quickly and potentially get a better result. So the total compute time just to make this one graph was 81 days because we were running on multiple VMs, running multiple trials of each test and taking the average. So there was a lot of work to be able to generate this. And this is sort of what we're trying to do with the Autotune as a product is cut all this down, but just having all this training data already collected for us. Whereas this one is training from scratch because we had no experience with Oracle before this. We didn't have existing databases running on the same hardware they were running at the bank. All right, so what are some of the main things that we learned? So as I said before, the machine learning models actually don't matter right now. Whether it's linear regression is not going to do this, but we have a Gaussian process model versus something more sophisticated, like reinforcement learning or deep reinforcement learning. We don't think it makes a difference right now, but potentially over time, as the complexity of what we're trying to tune increases, it could be the case. So I'd say I want to talk about these three other lessons that we learned. I would say also too that we also learned that the training data, the metrics that we're collecting, there is no privacy concern. The bank is super strict about security because obviously it's a bank, and so we obviously weren't allowed to have a direct SSH connection in and out of the bank. We had to send Docker files, run our experiments, and then they would upload the results to us. But like I said, they looked at everything we were doing, and they felt that the metrics of the database system were benign and they couldn't be traced back to anything that was sensitive. All right, so the first lesson we learned was sort of obvious to anyone that works in the tech field, is that people make mistakes, even experts make mistakes. And so what we found is that there were some obvious things that they should have tuned in this Oracle database, even though they had told us they tuned it, they just didn't do it. So in particular, there's 3 knobs here where there's sort of obvious things that they should have done that, these weren't the only things that made a big improvement, but these got you a pretty good chunk of the benefit. And so what happened was they had made a few years prior a sort of a mass migration from Oracle 11 to Oracle 12.2 across the entire company. And so they told us they tuned the database, which is true, but they tuned it back when it was version 11. But after that migration, nobody ever went back and tuned the Oracle 12 databases to be, for the knobs that Oracle 12 exposed you changed, how you may want to set certain things have changed. So, you could blame them like, hey, don't be stupid, don't do this. But again, they have thousands of these databases. They have different people that are in charge of them. It's a very complex bureaucracy because the bank has 100,000 employees all across the globe. So to go to every single person that that's controlled this database and say, hey, we want to spend some time tuning it, that's a very, it's a very complex human process to deal with. So what we think is the right solution to this is that the machine learning models we're using to actually make these recommendations, apply these changes, could also be used to do provide predictions about identifying what databases are not being configured correctly and what they should be, or what benefit you could actually get. So then you can begin the process of getting approval to actually tune the database, and whether by a human or whether by something like Autotune. Right? So Autotune can be a tool to help grease the wheels within the company to make these kind of changes. The next challenge was dealing with the workload replay. Again, as I said, we had a 2-hour trace. We only ran 20 minutes at a time. The application was like an internal Jira application or Jira site that they use for the IT group. Again, it's a huge bank. They have employees all across the world. So at all times of the day, this thing's just getting hammered. So the 20-minute slice we used was representative of pretty much the entire workload within the business week. And so the challenge, again, if you have this 20-minute trace and you have a bad configuration, it could end up being 2 or 3 hours to run it, to get it complete, because you always want to execute the same number of queries every single iteration. So now, again, if you have a bad configuration and the workload replay takes 4 or 5 hours, you're just wasting time because it's not good. It's not going to make anything better. And you want to sort of board it early and move on to the next configuration. So that's essentially what we added. We added ability to recognize that the configuration we're trying is bad. It's taking 2x longer than it should, and we go ahead and can kill it early, and then report back to the service that, hey, this was a bad idea, and get the next configuration. Repeat the process. Of course, now you got to have, in the machine learning side, now you got to be able to deal with these bad configurations. And there's 3 different scenarios where these can occur. So the first one I've already talked about, right, when you have a configuration that's just making everything run slow. The next one is when the database system will fail to start because of a bad setting. Like if you set a buffer pool, a memory buffer size to -1, that's an invalid value. The database system will catch that when it starts up, in theory, and go ahead and throw an error and crash. And then the last one is a bit more nuanced, where a configuration knob is set incorrectly, but the database system doesn't try to use it or exercise it until some later point after startup. So now you got to be able to figure out if the system crashes, 5 minutes into a run, is that because of something we've done in the configuration, or because something hardware is failing, or some kind of other environmental issue? So we saw this in Oracle. There's some knob that you set a buffer pool size for the JVM or something that's not the main buffer pool, and on startup it doesn't check that value. But then 5 minutes later, as it's executing queries, then it decides to try to allocate that memory, and it freaks out because it has an invalid value. So you basically need to observe the system if it crashes at some later point. Was it something because you had a bad config or something else going on? So then we've got to provide feedback now to the machine learning models to be able to say, hey, this configuration was bad, don't try it again. But we need to do it in a smart way so we don't screw up how the machine learning models explore the solution space. So again, I'll explain what that is. So how do we identify when there's a failure? There's no magic to this. In the case of for this Oracle database, we just scrape the log to see whether we can find an explanation or indication of what went wrong. We have a crash. So here I'm showing if you set the shared buffer parameter or knob in Postgres to a negative value, it freaks out, crashes, throw an error. So again, this is sort of the customization we have for each of our different database system to be able to recognize what these errors are and track them. But then now, how do we incorporate these bad results into our machine learning models so that we don't try them again? So if you read the machine learning literature, they would say to set the value of the objective value of the thing you're trying to optimize for a bad configuration to be the worst configuration or worst value of anything you've seen so far. So if I had a configuration that didn't crash, just performed really poorly, if something does crash, we just set it to be the same value of that previous bad configuration. The machine learning literature says maybe try 2x or 3x worse. In our experiments, we didn't see it make a difference. Your sort of first inclination is maybe set it to negative affinity, but again, that'll screw up how you do gradient descent in your machine learning models, and you don't want to do that. Okay, so before I jump into the next field study, Andre, do we have any questions?
Yeah, we actually do have a couple questions. The first one is, can your approach be extended to tune arbitrary system with configuration file?
Yes. So the question is, can we tune other database systems or other software systems in general? Yes. So we've done, I have one slide I can show real quickly. We've done tuning for the Linux kernel. So we just expose the Linux kernel parameters that you want to set for Postgres, to Autotune as if it was just another knob. It doesn't know, doesn't care. And this is just showing that should you tune the database separately, the OS separately, or together at the same time? So if you tune them at the same time, you get the best performance. We've been asked to tune the JVM. We've been asked to tune other NoSQL systems or non-relational databases. Again, it doesn't matter. It's just numbers. Our focus right now is on Postgres and MySQL, just because, one, I love databases and I love those databases, so all my energy is in that. So the answer is yes. It's not on our radar right now.
Okay. Oh well, questions are coming. What's the story behind the name Autotune?
So Autotune is just a play on the words of Autotune, right? So Autotune is like the what they do now with like singers, the pop singers. They have a way to correct the pitch when they sing, and that's called autotuning. So it's a play on that word.
Okay, the next question is your focus is mostly on cloud deployments, and people are wondering, what about on-prem? Some knobs are at the OS level, and some other knobs that require database to be turned into maintenance mode. How do you address those?
Yeah, so the French bank, that was on-prem. Again, it was in their private cloud, but from our purposes, it was it was not running in AWS. So maintenance mode is sort of like restarts. We'll talk about that in a second. But you have to have the right permissions in order to set the knobs that you want to set. I don't think Amazon, at least on AWS, I don't think in other systems, I don't think they classify or they categorize which knobs different user permissions are allowed to tune. I think you're allowed to tune all of them. For the maintenance mode thing, again, you have to have permissions. If you want to be able to set the knobs correctly and make it and be sticky, persistent, then you have to have the right permissions. So Autotune assumes that's set up.
Okay, next question is about high availability. From your opinion, is Autotune applicable to a system with high availability requirements? Did you ever interfere with cases when Autotune may lead to performance problems or even crashes with never before observed requests?
So the question is, how does Autotune work in a HA high availability?
What if you compromise high availability with some of your knob tuning?
Yeah,
accidentally.
So we've been asked to tune read replicas versus the primary writers, the write primaries on AWS. Of course, the tricky thing is that anytime the read replica could get promoted, and therefore you have to change configuration. The current version of Autotune is not sort of cluster topology aware, that it knows that something's a read replica and that it's attached to some other primary node. It treats them as separate databases, but eventually we want to get into being able to do that. And this matters for RDS. The other comment I'll say too is that we tend to be very conservative in how Autotune modifies these configuration parameters. So what that means is that there are some knobs you can set that will make the database run really, really fast, but you could either end up losing data, like, if you turn off fsync, of course the database is going to run faster. And machine learning models will learn very quickly that turning off disk writes make your databases run fast, because it doesn't know that if there's a crash and you end up losing the last 10 milliseconds of data, that there's an external cost to losing that data that now the organization, the company has to deal with. That's not something machine learning models can deal with, because that's an exogenous factor or external factor. So what we've done is we've gone through the documentation for Postgres and MySQL, and when we did this for Oracle, same thing. And we looked at every single knob by hand and just determined us as database people, will this knob put the database in a state where we can end up losing data or end up causing crashes that cause problems? And if yes, then we either don't tune it at all, we put it in our deny list, or if there's certain parameters like the disk write, whether fsync, yes or no, like if there's certain values that could cause this, then we cause this problems, then we disable that as well. So I would say Autotune tries to be very, very conservative, making sure that people don't lose data when they're trying to get better performance. The restarting issue, that's a separate thing that we'll talk about in a second. But in general, like we try to avoid those issues. We have not seen anything come up.
Okay, the next question is, because there are like a lot of databases, and you mentioned that basically for Autotune, everything is just numbers and you can configure and tune anything. The question is, like, do you have any plans to make open connectors for community-led expansion, so people can just plug in their favorite database and feed data to the Autotune to tune it?
It's not on our radar right now. There was a startup called SigOpt that got bought by Intel that sort of had that approach, like an open API where people write their connectors. Again, like I'm hesitant to do that, because unless you know what you're doing, you can put your database in a bad state and end up losing data. And I don't want to be, I don't have that over my head. I don't want people to blame me for that. So it's not something we're considering right now. We've had enough interest in just Postgres MySQL by itself that actually SQL Server is probably the next most requested database. Beyond that, we'll eventually get to those other systems, but I think I'd rather do a really good job on MySQL and Postgres before moving on other things. And even then, we probably still stick with databases, right? Not the JVM and not Linux, and even though we could.
Okay, these are all the questions so far.
Okay, awesome, cool. Great. All right, so the next field study I'm going to talk about, this was actually with Booking.com, again, another European company. They actually reached out to us before the pandemic and said, hey, look, we have this huge MySQL fleet running in their data center in Amsterdam, and it was already tuned by their in-house MySQL experts, but they want to see whether Autotune can make things better. Then the pandemic hit. Their main contact there disappeared, came back up in June, July, and was like, hey, look, people aren't traveling as much. We need to start saving money. They want to use Autotune to try to reduce their server footprint. And so for this, we were actually going to run in their production database. So we're going to be running on read replicas. So these are not the databases serving the actual the Booking.com website. These are for the back-end internal services of their analytical team and other portions of the company. So what they already had was this Puppet-based rule-based configuration scripts, where every time they deploy MySQL on a new box, the Puppet script would look to say how much RAM it had, how much CPU it had, and then again, similar to PGTune or the other rule-based tuners that I talked about before, it would set some knobs based on what it knew the hardware was. So for this, we're going to actually now tune 23 knobs in MySQL. And actually, they went from MySQL 5.7 to MySQL 8 because MySQL 8 made it a lot easier to set knobs and have it be persistent. Like you could do this through the SQL interface and didn't have to SSH into the box. And MySQL 8 also exposed much more rich metrics through the performance schema over what MySQL 5.7 had. So they were looking for a reason to upgrade to 8, and Autotune was helping them push them along. And MySQL 8 has been great for us. So for this one, they didn't want to optimize performance. Again, they wanted to reduce the hardware consumption of the database to be able to turn off machines. So they wanted us to have basically the same P99 latency for the queries that they had before, but the way they used to measure hardware consumption for the database was the number of concurrent threads and the overall CPU utilization of the database itself. The other challenge we had to deal with too is because these are running in production, they only wanted us to tune the database between 9 and 5 during the day when the DBA we were working with was on pager duty, and then we were only allowed to do one restart per day. So we had to then expose some knobs or expose these additional configuration parameters through the Autotune service to restrict it to only tune within this time window. So now, as I said, unlike in the bank's case, we were running production. And so that means we didn't have a way to reliably put the database back to the same state over and over again, and then run the same workload trace over and over again. Because we had no control of what queries were coming to us because they were being sent up from the application up above. So now we need a way to know, are we actually making things better or not? Because we can't assume that we're running with the same environment over and over again. So for this, we actually had to look at two databases. We had, again, similar to the demo we're giving today, we had the one database that we're going to tune, and then we had a control database where we're just going to monitor it, don't make any changes with it, have it use the same configuration that the tuning database started off with. And so although at any given point in time, they're not running exactly the same query, but over the course of days and weeks, the workload would be on the two boxes would be similar enough. We can use that to gauge whether we're making things better or not. So in the first step for the driver of the agent, it would connect to both databases and collect the runtime metrics. And for this, we're using a combination of the InterDB stats the data system generates, as well as getting OS level metrics through Telegraph. Again, similar to going to get these things from CloudWatch if you're running in AWS. Then we would just wait, right? There's nothing to do. We just let it go, sit there, and let the queries arrive and be able to execute them. And then we go, after a certain time period, we go collect the metrics again, compute the delta as we did before, ship this over to the Autotune service, and then it crunches on it and then generates a new configuration that we then install into the tuning database. And then if this was the one time in the day where we were allowed to restart the database, we would go ahead and do that. So here I'm showing the results of this deployment for actually two databases. It worked so well for the first one that they had us try it out on a second one. So across the board for this first one here, you see that we're keeping the latency roughly about the same. We're only seeing a 1% reduction, which is pretty much nothing. But we're seeing a massive reduction in the number of CPU utilization and the number of running threads. So the back of the envelope calculation for this says that with a pool of 20 to 25 replicas, if we can reduce the CPU utilization by 25%, you can potentially turn off 2, if not more, machines in the pool and have no reduction in the quality of service that they're providing to the applications up above. And at Booking.com scale, turning off 2 machines per pool times hundreds of pools, that's a pretty big savings for them. For the second database here, we see a much more larger reduction in the P99 latency, but a small reduction in the CPU utilization. And this is because, as you can see here, the utilization was 8%. This box is just not being stressed as much as the other box here. So even though we were able to tune it to reduce the latency, we're not seeing as big of a win for the hardware metric that they cared about. And so this is because this machine was actually this pool was not being hammered as much as the first one, and it's something that they were not aware of because the monitoring alerts look for wild aberrations. Not that the things just got less busy. So again, Autotune is a good example where the target metric they wanted, we were able to optimize when you push a lot of queries to it. But if you're not pushing that many queries, there's still some benefit that you can achieve. All right, so I want to talk about 3 lessons learned here real quickly. So the first one we didn't expect is that we were going to have to deal with external factors and how people configure their databases that are not immediately apparent to, or can be even apparent at all to the machine learning algorithms themselves. And this is similar to the external costs that we talked about before. Like if you lose data, somebody up above is going to care potentially. There's certain things that they had in their sort of internal IT protocols of how they were configuring the database system that Autotune simply was not aware of. So in the example here would be how they set the InterDB buffer pool. So when Autotune looked at the buffer pool, it decided to set it to be roughly about 80 to 85% of the total battle memory available to the system. And oftentimes when we go see customers, they're already doing this, because if you go look at the documentation of those blog articles that say how to tune MySQL, there's always going to say, hey, the conventional wisdom is to set the buffer pool to be 70, 80% of the amount of memory that's available on the box. But they were actually setting it to be half the amount of memory that was available on the box. And so we asked them, like, why is, the box has 128 gigs. Why are you only setting this to 64 gigs? Well, it turns out there was an IT policy that every database instance was only allowed to use half the amount of memory that was available to the system, because they were worried about some flood of queries coming up above that was unexpected, and then MySQL was going to run out of memory if it tries to create too many network connections. So they artificially always set this to be lower than it actually should be. But the guy who came up with that policy was no longer there, and they sort of forgot about it. And so, whether or not this is the right thing for them to do, this is something that they have to figure out, not something Autotune agrees about, although Autotune tells them that they should be changing this. So the way we handle this now in the Autotune service, as you saw when I set up the demo, we now expose to you an API that allows you to set the boundaries to set different values. So if you know certain things like the buffer pool size should not be more than half the amount of memory, you can go ahead and set that in the on the service, and then the models know not to exceed that boundary, because that's a hard constraint when it comes up with new configuration recommendations. And the machine learning models handle that just fine. The next issue is how to deal with restarts. So as I said, some knobs don't take effect until you restart the system. So no database system is immune from this. So MySQL and Postgres, there's a larger number of knobs that require a restart than in the commercial systems, but the commercial systems still have it. And of course, nobody likes downtime in the database system. And furthermore, sometimes if you set the knobs a certain way based on what they were before, then you can come up with the restart time could be unexpectedly larger. So the example I always like to use is the MySQL log file size. If it's currently 5 gigs, you set it to 10 gigs, you restart, come back up. It says, oh, I used to be 5 gigs and now I'm 10 gigs. I have enough space. I don't need to do anything. But if you're 5 gigs and go to 1 gig, then it has to start compacting the log and before it can actually turn the system on and start running queries. And how long that's going to take depends on many different factors. So that was one of the challenges we faced, was like they wanted to know, if I restart, how long does it take for me to come back up? And we didn't have an easy way to tell them this. All right, so how do we solve the first problem? I don't know what that dot is. We can ignore that. So the first problem is, how do we know when we're allowed to restart? As I said, this is not something that we can reason about through machine learning models. We now expose an API in the service and say, here's the time ranges when you're allowed to restart, and then within that time range, how many times you're allowed to restart, or when is maybe you're not allowed to restart, right? And so we now expose all this information to you through the service, and the machine learning models know how to account for that. Like if it says, if I'm in a time period where I can't restart, then it knows not to try to tune knobs that require a restart. How do I figure out and show the human how long it's going to take to complete the restart? This is actually an open problem. It depends on a lot of factors, as I said, and we don't have a good answer for this just yet. But we think the idea is, again, train another machine learning model that can learn the restart time based on different parameters. All right, so the last issue is the thing we talked about before, is having a reliable baseline. And again, if you're tuning the live database in production, we need a way to be able to say, are we making things better or not? Because we can't assume that we're running the same workload over and over again. The one thing that we found during this work is that most people don't have sample workloads or have the ability to collect sample workloads that they can run in a staging environment. They're basically, some basic tests they run on staging before they push things in production, but they don't have query capture traces. The challenge also with this, if you're now running production, is that you need to know for at any point in time, is the workload I'm looking at similar to the workloads I've tried in the past, to know whether the configuration or the benefit I'm getting at this point in time is actually correct or not based on what I did in the past. So what I mean by that is, so this is a workload trace from one of our customers, and what you see in this sort of box here is that all of a sudden the workload increased by 20 to 25%. The number of queries they were executing per second increased by 20 to 25%. So we would see now an improvement in throughput, or maybe a reduction in latency. And we had to figure out, is this because of it's a bad configuration, or is this because the workload has changed? And so we see this all the time. This is also what the tuning schedule helps with. Like, I don't want to try to tune it at midnight if no one uses my application. I want to tune in the window where I know I'm getting my regular workload. So this is also an open problem. There's some time series analysis we can do to identify what things are similar, but we think the long-term solution is going to be potentially a workload synthesis tool where we look at your database, look at the metrics, and then it can automatically derive a workload that when it runs on the database system, it exhibits or it exercises the different parts of the system that produces the same metrics, so that we can run a bunch of experiments on a staging database before pushing things into production. All right, before I jump to the last part, is there any questions from the audience for this?
No, so far there are no additional questions.
Okay, so now beyond databases, we were asked, so far, like, hey, can you tune other things beyond databases? And the answer is yes, but that's not what I care about right now, right? Databases are my favorite thing in the world after my wife. Like, it's just databases. And I think again, these are really complex pieces of software. It's the most, oftentimes the most important thing in any application stack. And, there's not enough humans out there to be able to, there's no time for everyone to tune every single database correctly. So we think an automated solution like Autotune is the way to go. But in my opinion, though, the problem is that just having a really great database configuration tuning software or optimization software is not enough. There's other things we should be doing just beyond database tuning to make Autotune be a household name and things that something that people are really interested in. So as part of this year, in addition to announcing the new Autotune service, we've also launched Autotune Records, where this is a record label that we're putting out what we think is the greatest hits, the best music for database and auto related latest hip hop beats and street music. So we have a Bandcamp page. Everything's on Spotify. So I encourage you to go check it out. And this is where I think the big direction where Autotune is going to go. It's not tuning the JVM. It's in music. So I want to talk about the two albums we put out so far. The first one we had come out in May. This is OKA. This is actually live otters we put in a studio. You had to feed them fish to get them to get all excited, but we put them in the studio and we got them to rap over hip hop beats. This one this is the one I'm most excited about. So that's out on Spotify. We had vinyl records, but they sold out, but it's available on iTunes and a bunch of other things. And then last week we just put out a new hit single from Stripper Lord. This is a bit more melancholy. This is like music if your database is failing and having corruption problems. It's music that kind of gets you in that mood, understands the problems that you're having. So again, everything is available online. We encourage you to go check it out. All right, so what did I talk about today? So I showed that how we can use machine learning to solve some of the problems in automatic configuration tuning for database systems. There's other things that we had to deal with, like through the non-machine learning interface, but recognize when things go bad or in order to interact with data in a certain way based on how organizations are using it. But we think this is the way.
Энди, ваша база данных теперь оптимизирована и готова к использованию.
Okay, awesome. I always forget to do that. All right, so let's go back and check on our demo. I'm assuming that's correct Russian, right?
Yes, that's good enough.
Okay. All right. So, so here's our tuning database. We can log in and we can see different configurations. Let me zoom out. That's probably. Okay, sorry about that. Right. So here's the list of all the configurations that it's had. So we can click on one and you can see what it's tuned. Then we can also compare it against the first database. So it'll show you how Autotune is changing these parameters here, right? So then now we can go into our performance charts. It's full screen, right? So here's the performance of the database over time. This is what it was in the first configuration, and then this is what it's up to. But we want to be able to compare against the monitoring database, that's the control database, to see how much better we're doing through Autotune tuning the database versus just using the default configuration for Amazon. So we go ahead and edit the chart, and we can add our monitoring database to this. It's running the exact same TPCC workload. We load that, and you see here again, this one's doing roughly around 1,500 transactions a second. And then at its peak for Autotune, the Autotune optimized database, we're getting 2,500. So far, we were able to increase the database performance little less than 2x or 3x, a little less than 2x. But again, this is just in the beginning. Over time, as Autotune understands what the application is trying to do, it'll get better performance, and eventually it'll converge and recognize it doesn't need to tune anymore because there's not much more benefit that can be achieved for the given workload because it's confident that it has produced the best configuration. Okay, so with that, I'm happy to answer any questions.
Okay, unfortunately we're out of time, so for the questions we have to go to discussion zone.
Okay.
So yeah.
Okay.
So if anyone has any questions, join the Zoom link with the discussion zone. We're going to continue there. Thank you, Andy.
All right. Thanks so much,
See you
guys.
in a bit.
Yeah.